Hello, welcome back to the lecture Biological Wastewater Treatment. Today we will talk about the kinetic of biological reactions. With the last lecture we have learned what type of microbiological reactions are important for wastewater treatment. Now we want to learn how fast this will be going. As the first part of this lecture we will have a look to the enzyme kinetics. There you will learn something about your reaction kinetics and some interesting biological things. Normally biological reactions are occurring at moderate temperatures and they are catalyzed by so-called enzymes. Enzymes are proteins with functional groups where the reaction energy for an enzyme catalyzed reaction will be reduced so that the partners can react. A long time ago, 101 years exactly, two nice guys, Michaelis and Menten, has supposed this key principle of enzymatic reaction. Normally one substrate reacts with an enzyme where finally the key enters in the log and forms the enzyme substrate complex, where the enzyme is transferred to a product and then the enzyme is released. The main idea was that the formation of the enzyme substrate complex is an equilibrium reaction, but if the substrate is changed to the product, this is irreversible. Now, finally, there are some kinetics as well where this is not the case. But we will go ahead. Now, this idea we have to translate in a chemical reaction equation. This looks like this. That's an enzyme plus substrate reacts with K1 plus to enzyme substrate complex, and the enzyme substrate complex reacts with another speed constant K2 plus to an enzyme and product. And finally the enzyme substrate complex can also react backwards with the constant K minus 1 to the enzyme and substrate. And as we see, if this is irreversible, then the reaction rate of the product formation due to chemical reactions kinetic we can express with this equation. This speed constants are multiplied with the concentration of the educts. And in our case, the product formation is the same as the substrate uptake rate. Now, I'm always using positive numbers within these approaches, and if there is a negative sign required, I will take care in the mass balance of this. Finally, what is going on? The main idea is that after starting the reaction, then we are using this Bronsted quasi-stationarity condition. That means that the formation of the enzyme substrate complex and the reaction of this should be the same. Therefore, we have seen what is the production of the enzyme substrate complex is only going to this form. Therefore, this is K1 plus multiplied with the concentration of the substrate multiplied with the concentration of the enzyme. And the reduction of the enzyme substrate complex is with respect to the backwards reaction, K1 minus concentration of enzyme substrate complex, and as well K2 plus. And with this we can express the concentration of the enzyme substrate complex with the concentration of the free enzyme. And finally all constants are formed together to one constant, Km, due to Michaelis-Menten, where Km is this concept, this speed constants. Now the main idea, this is for other kinetics as well, as we will see, is that we are looking what would be the maximum possible reaction rate. And there we see we have the total number of enzymes, and they only have two forms. In our case, the free enzyme and the enzyme substrate complex. And then if we are thinking what would be the maximum substrate uptake rate, with respect, this would be if every enzyme is there in the form of an enzyme substrate complex. And this is here finally K2 plus multiplied with CE plus CES. Yes, and knowing this and this, we can bring this in relation. And there we have that the relation of the substrate uptake rate to the maximum substrate uptake rate depends on the enzyme substrate complex and the total enzymes. The speed constant K2 plus is eliminated in this way, and now we are expressing the enzyme substrate complex with this form where the free enzyme is included. And there we see we can eliminate the concentration of the free enzyme, multiplying by Km, and this is resulting in this so-called Michaelis-Menten kinetics, where the uptake rate could be reached a maximum uptake rate, where the concentration of the substrate is a lot higher than this coefficient Km. The next slide is showing the illustration. Also finally, we don't have a first order reaction kinetics. We have also no zero order reaction kinetics. We have something in between. This is the monotype kinetics. We will see earlier. This value Km has a special meaning if this has the unit of a concentration. As you see here, if the Cm and Cs, also the concentration of the substrate, has the same amount as Km, then we see that in this case the uptake rate reaches half of the maximum. Now for high substrate concentrations we are reaching the maximum uptake rate. For very small substrate concentration, the behavior is similar to the first order reaction kinetics. In this case, Km is a lot bigger than Cs, and then we have first order reaction kinetics. In the wastewater treatment, unluckily, we often want to have very small concentrations, and therefore we have small uptake rates. But finally, this is the easiest and poorest way, but life is more complicated. Many things may happen. In this case, maybe our process can be inhibited from an inhibitor. And there are different types of inhibition important in wastewater treatment. One is a competitive inhibition. Also the enzyme has one lock for the substrate, but maybe the enzyme matches as well. And there are different forms. Also, if the inhibitor is locked in, the substrate cannot, and so on. There is some competition. And this we can also express in a kinetic approach. Also finally, that what we had beforehand is the same, but the enzyme can also react with the inhibitor to the enzyme inhibitor complex. And there are also two speed constants. And finally, for the uptake rate, this is the same as before. And we can formulate the Bronsted quasi-stationary condition as well for the enzyme substrate complex and as well for the enzyme inhibitor complex. Also there, the speed of formation, the speed of deformation should be 0, and here the same. And there we can calculate the concentration of the enzyme substrate complex as a function of the free enzyme concentration. This we had beforehand as well, and the same we can do for the inhibitor concentration. And there is another component Ki there. Yes, and in this case we also formulating our total enzyme concentration. Now we have 3 species, and the maximum uptake rate is consequently as well given with these three species. And there we are putting in our enzymes and replacing the concentration of the enzyme substrate complex with this expression, and the concentration of the enzyme inhibitor complex with this expression. And finally, we can see we can eliminate the concentration of the free enzyme, and multiplying everything with Km leads to this form where we have the competitive inhibition, where the inhibitor concentration plays a rule. If this is 0, then we have the normal Michaelis-Menten kinetic. If this becomes bigger, then we will see that the Km value seems to be bigger. Also finally, the curves with growing inhibitor concentration becomes flat. This would be the inhibitor concentration 0. But finally, for very high substrate concentrations, we still reach the maximum uptake rate. But we have unluckily as well non-competitive inhibition. In this case, the inhibitor can lock in another place in the substrate, and if this happens, the substrate cannot be locked in. Also we can also see here, if the inhibitor is in, the substrate has no place. Or in this case, the substrate cannot be released. Only this form would be the suitable form. Here we can translate this as well in our chemical structure. There we have the case that the enzyme substrate complex as well can react with the inhibitor. And there we have the enzyme substrate inhibitor complex as well. And there we are going the same way. We are formulating for all enzyme forms the Bronsted quasi-stationarity conditions. And for the enzyme substrate inhibitor complex, we have the formation and destruction should be 0, and this leads to the fact that the CESI can be expressed as a function of the enzyme substrate complex. For the enzyme substrate complex, we have here as well the interaction with the inhibitor, but from this equation we know that these two terms are together 0. Also here we can see this here, and therefore this is leading to the same equation that we already know from the former formulations. There we can express the enzyme substrate complex in the same form. And then we have, of course, the enzyme inhibitor complex, which comes out the same as beforehand. Yes, and we can replace the enzyme substrate complex concentration as well with this expression, and there we have this nice expression where the enzyme substrate inhibitor concentration only depends on the free enzyme. This is in this concept quite important because we want to remove it. And of course the maximum uptake rate depends on these 4 species of enzyme, and we are formulating this equation in the same way and replacing every term with the facts that we can get out from the Bronsted quasi-stationary conditions. And this leads to this expression, and we see we can eliminate the free enzyme concentration, and if we are multiplying everything with Km, this leads to this expression, where the inhibitor, if this is 0, then we have the normal Michaelis-Menten kinetic, but if this becomes bigger than 0, then we have a reduced uptake rate. And in the special case that this Kii and Ki is the same, we can express this in this way. And this is the form which is widely used in wastewater treatment. Finally we see in this case not only the Km is shifted, mainly the maximum uptake rate becomes slower if there is an increasing inhibitor concentration. If the inhibitor concentration is 0, then we have the normal Michaelis-Menten kinetics. But finally, the maximum rate is reduced in this case. Yeah, we have also cases where the enzyme-substrate complex reacts with a substrate, very fine substrate, and forms an enzyme S2 complex. But the product can be only formed with this reaction. Yeah, this happened as well, and there we are formulating the Bronsted quasi-stationarity conditions for this enzyme S2 complex, and this leads as well to an expression with the enzyme substrate complex concentration, and then we are making as well the Bronsted quasi-stationarity condition for the enzyme substrate complex, where as well the reaction to CS2 occurs, and we see this difference is 0, and finally we can eliminate this, and it comes out the same as we always had. And now we only replacing this concentration CES with this concentration CES, and then we have another expression for the enzyme S2 concentration. And now we are mixing up together. We have 3 species of enzyme and can formulate the maximum uptake rate in this way. And here we are replacing every term with what we had found from the Bronsted quasi-stationarity condition. And this is leading, as we can see, we can eliminate CS multiplying with Km. And finally this leads to this expression where Km and CS, and there is another term with the square of the substrate concentration. And this looks in this blue way in comparison to the monotype. The characteristics is that we have a maximum uptake rate, and for higher concentration the uptake rate goes down. Now, this is a quite dangerous behavior in wastewater treatment. If we are reaching this point, the process becomes unstable. Because finally, if the concentration due to some circumstances is growing a little bit, the uptake rate goes down. That means finally the concentration is rising more, and so on, the process crashes. And this is highly unwanted. Therefore we know we have to be very careful. One good example is phenol. Phenols are behaving like this, but as well acetic acid in the anaerobic digestion, and ammonia in high strength ammonia wastewaters, or nitric acid. Yeah, we have another thing. You don't have to learn all equations by yourself, but only an illustration. Sometimes we don't have only one substrate that is transferred. We have 2 substrates that are brought together. In the introducing picture or illustration of the enzyme, there was made the reaction of 2 substrates with one enzyme. Typical is the reaction with oxygen. Finally the substrate is oxidized, and there we need a substrate and oxygen. And here we want to analyze this in a kinetic way. What is the influence of these components? And finally we can formulate this nice equation that the enzyme and the substrate 1 and the substrate 2 forms the enzyme S1, S2 complex, which releases to the enzyme and the product. Yes, and the idea is to formulate all these equilibrium states, which is resulting in constants K1 and K2 depending of the substrate 1 and substrate 2. From the Bronsted quasi-stationarity condition this comes out. We are doing the same for the enzyme S1, complex reacts with S2, and there we are formulating the 1,2 coefficient, and vice versa. The enzyme substrate 2 complex can also react with the S1, formulating the S1, S2 complex. Yeah, and finally we have the concentration ES1, S2, and this has to be equal. There is following directly that K1 times K12 should be the same as K2, K21, because this has to be the same. And now, we are formulating our total enzyme concentration consists of 4 species. We are formulating the maximum speed, and there we have this expression, and then we are putting in our findings, and then this is leading to this expression. And finally, under the consumption that K1 is equal to K21 and K2 is equal to K12, then follows this well-known so-called double substrate kinetics, where with the so-called monotherms, the substrates are bounded multiplicatively. This means if there is one substrate missing, there is no reaction. As an example, an aerobic process like nitrification, if there is no oxygen, there is no reaction. If there is no ammonia, there is also no reaction. And finally, this is widely used in the wastewater treatment to describe these procedures. There is another double substrate kinetic in the literature. Maybe you have a look. It could be the case that one enzyme can react with 2 components. And in this case, the reaction is a little bit different. Also finally, if one enzyme can react with glucoses and fructoses. And if there is a high concentration of glucoses, then they are working with the maximum uptake rate. And if there is additionally also a high concentration of fructoses, they will not work double the speed if they are the same magnitude. In this case, the other substrate acts as a competitive inhibitor, vice versa. And so the total uptake rate is maybe reduced, or growth rate. Not to confound this. Yes, there are other dependencies of the enzyme kinetics. Also one important stuff is the pH. The pH can influence the activity of enzymes, and these are depending very much on what enzyme is used. The idea behind is that the enzymes are polymers of amino acids. And finally, due to this fact, there are some ends, also where there is carbonyl groups and this amino groups. And finally, they can be there in a positive form, where here the amino group has absorbed 1 proton, and this can be released. Also 1 proton can be released, and then we have a neutral form, and they can release even more, and then we are providing the negative form. Yes. And normally only one form, also in this case the native form, is the active form. And so we can formulate an activity coefficient. This depends on the native form with respect to the positive, the native, and the negative form. And now we have here to calculate from these equations and the acid constants what comes out. Also finally the acid constant for the KS1 is defined as this, the native enzyme multiplied with the HO3 plus, also the products divided to the adducts. The water concentration is not mentioned, is K1, and the same is here. The products, the E and the CO2 with respect to ES is KS2. Yes, and finally, with these equations we can formulate the species of the positive charged enzyme and the negative charged enzyme with respect to the native enzyme. And that is, we are mixing together, and then we see we can remove the concentration of the native enzyme and introducing the pH, which is a negative logarithm on the base of 10 of the concentration of Hg plus ions with respect to 1 mole per liter, and as well the pKs, which is the same with the Ks value as well with a unit of 1 mole per liter. Then we can formulate this equation, that this is 1 divided of 10 in the power of pKs1 minus pH plus 1 plus pH minus pK2. Normally this is a quite low number and this is a quite high number, so this power is always quite negative. But we will see the behavior. One example, pK1 is 3.5, pK2 is 8.5, then the activity is due to a range of several pHs nearly 1. But if they are narrow, they only have 1 unit in between, then we have an optimum, a very defined optimum of a pH. And we don't reach the activity of 1 either. So this is always reduced. In this case we have, for example, with methanogenic bacteria, there it's quite narrow. Another important influence of biochemical transformations is the temperature, as in every chemical reaction. Normally the Arrhenius equation applies, where the maximum uptake rate depends K0 with the exponential of the activity energy, the universal gas constant divided by T. But enzymes are not like other chemicals. Finally, they can change their behavior with respect to the temperature. As you know maybe from egg, this is clear, and if you heat it, it becomes white. Finally, a native enzyme can be denaturated. And under equilibrium conditions, in this case, the concentration of the denaturated to the naturated is Kd. And the total enzyme concentration is the native and denaturated enzymes. And then we can calculate what is the amount of native enzymes, which are important for the uptake rate. Then we have this expression, that's the total enzyme concentration divided by 1 plus Kd. Yes, and this equilibrium of Kd, the form of the denitrification, depends as well exponential on the activation energy for the denaturation effect, and also there is a change in entropy due to denaturation. In this form we can express this coefficient. And so we can express the temperature dependency with this numerical constant K0, and then we have sometimes the total enzyme concentration can be brought in, but finally this depends on one exponential term with the activation energy, and then there is another, some empirical factors B with the activation energy of the denaturation. But last not least, in the wastewater, normally we don't have a very wide temperature span. Sometimes we make it a little bit easier. For the temperature range between 10 and 30 degrees centigrade, we make a simple approximation. Two concepts are used, that we have a reaction rate for a special temperature, in this case 15 degrees centigrade, and the reaction rate with respect to the temperature is multiplied with an exponential term, theta times the temperature that we want to apply minus this base temperature. Sometimes this is also changed as the temperature is multiplied with a factor bigger than 1, of course, a little bit bigger, to find the temperature, the uptake rate with respect to the temperature. The values f in this case are between 1.05 to 1.12 depending what type of reaction, or theta is between 0.045 to 0.12 depending on the reaction. Okay, this would be the case for the enzymes. Here is a typical sketch. Normally the temperature is sketched as a reciprocal, and then in the logarithmic scale of Rs it should be a straight line. Also finally the temperature goes up in this direction because it becomes smaller if the temperature becomes higher. And this is from the Arrhenius equation what we are expecting, and we see normally after a special temperature then the uptake rate drops down very dramatically. This is what we are observing. Yeah, this would be part of the next video. This would be too much in one video, and therefore I am saying goodbye, and maybe you can enjoy the next video as well.